So I want to get a little bit into the details. So for my person, as Martin already said, my name is Axel Schmidt. I'm working as Senior Technical Marketing Manager, so I'm more prone to the technology than the commercial things. And I'm located here in Germany, in Rosenheim, close Munich. And I'm in charge of the German OEMs like BMW, Volkswagen, Audi, and Daimler. And beside that, I'm also supporting some of the suppliers. All right. So what's the topic today is actually, so we talk about DC link capacitors. We have different families, and you know that's not something that's a serious flow. That's more something we cover several aspects. And one of them, when you talk about DC link capacitors, in really most cases, not only one capacitor fulfills the needs that you have. So you have to do a design to put a couple of them in series, and then you have to numbers of parallel. That also something we would like to discuss a little bit. And then, of course, one big aspect is power calculation. So how do I get my stuff running without burning it down or get very hot and damage some other component? The DC link, so that is what you typically get from marketing guys. So that is something that this is fancy kind of, you know, pictures that should show you somehow how that stuffs work. But in my mind, it, you know, we never get into the point of the thing. So, but what we can take out here of this is you have you have some source, and it could be either AC power source, but could be also a DC or battery, whatever. And then you can probably miss in that second case the AC-DC converter. So you have a DC voltage between the input and the output. And what you can do is you can either change the voltage level, the frequency, or both of them. So that's the major thing. And the DC link capacitor that helps you to get a stable operational mode. And so you don't suck in terms of you get a very high ripple, or your load draws more power than your circuit can probably deliver on that case. So that is the marketing thing. I'm more technical oriented, so that is the way how I like it. So you have some kind of a switched mode, and that is what is very common today and has some impact when you choose the right passive component of that. And that's not only about capacitors, it's only true for the inductors as well. So we have either an AC or a DC input. It could be a battery, or could be the 3-phase on the grid, or 1-phase. It doesn't really matter. But you need to have a rectified voltage, a DC voltage level in this schematic between this input and output, where the DC link is connected. And then typically you have, this is here as a 6-pulse bridge, could be also an H bridge. And there's some control unit we didn't talk about in this presentation here. So that controls the switches and switch it on and off, so that you get a certain voltage level and a different frequency. That probably helps you to drive a motor, so you have a rotating electromagnetic field, or with some DC stage behind the stuff, you can fill the battery of a car, for example. So the question, I think the first question that I have when I'm looking on this kind of designs is, okay, how much capacitance do I need? And actually there's a pretty simple way how to do that. So you need to know the power that your application is drawing, and then you have some time relations that could be either the switching frequency of your unit or some kind of hold up. The system needs to provide a certain power for a certain limit. Well, what I did here is I take 750 volt, 50 hertz system in an industrial area. And then, so the capacitor should be able to cover 5 cycles for 20 milliseconds. That gives you the delta T here of 100 milliseconds. And then you need to know, of course, the voltage level you're operating. And that's the nominal voltage on your system. And that's the allowed ripple on top of that. And the ripple means peak to peak in that case. So with that, you can calculate the capacitance you need for a DC link. And what you see here in that specific case, it's coming up to 6.111 millifarad. This level could easily change depending on your application. So if you go for higher switching frequencies, or you go for industrial solutions at a lower voltage level, 230, 380, or that respective now it's 400 volt. Then this can change easily. And I think the amount of capacitance you need gives you some idea about which kind of technologies you can choose. And what we have in our portfolio is actually, I think the most common one is the film capacitor on one side and the aluminum electrolytic on the other side. So these both are competing a little bit in certain areas. And then in the middle, we have a new one, what we call paraceramic thing, so K-sealing in KEMET language, which is pretty new. It's 3 or 4 years old. So you can choose that for a specific range of applications that driving with or coming along with the new technology, silicon carbide and gallium nitride sinks. So think a little bit about this dieseling aspect. So the first thing that you probably realize is, that's a kind of simulation. So we have a battery, so the DC on one side, and here is the DC link. And then in that case, we have an H bridge, which drives a single phase motor here on that case. And so what we do is we have a certain switching frequency here that create or switch on and off. And what it happens with that, when you put that on and off, you have a certain current through the motor here. And the thing that's very important here, that's not any more sinusoidal. I mean, that is whatever waveform it is, but it's far away from that. And one aspect is that all this calculation we done and all the tools we give you assume that you have a sinusoidal waveform. And that's not any longer true. And now we will guide you a little bit through that, how we can manage that and how we can get over this topic. Then we have a DVDT aspect, which is in sinusoidal waveform, a very smooth one, so it's not a big deal. But if you switch in a very fast time, a very high voltage, let's say, for example, 1 microfarad, you switch in 1 microsecond, and you have 800 volts, and then you have 800 amps peak current at the beginning. And that will probably kill most of the parts. So that is something we need also to keep an eye on, is the DVDT that really happens with the switched mode applications. Then the allowed ripple, I've already talked about that. That has a certain impact on the capacitance you need. We want to smooth out the voltage. That means we don't want to have this high frequency content that happens when you switch the stuff. Then overshot is also one thing that you can use for damping it. And spend more energy on that, because the overshot forces you to choose semiconductors with a higher rated voltage, even you don't need that, just because of the overshot. And that probably increases the cost of your application. And of course, we need to provide enough current, and that is what the capacitance at the end of the day is doing. And then lifetime, of course, typically in industrial application, we don't talk about a handy lifetime, about a year or two. So we talk really about 10 years and more. And so what can we do with this and this range? So one thing that we give you in lifetime is a 3D dimensional space. And within that 3D dimensional space, you can move, around 50–20%. So one portion is definitely the applied voltage to the rated voltage. This is in other words, which is the electric field or stress in the dielectric. And the second one is the temperature, of course. So typically the combined, the inverse power law and the Arrhenius. So that here is the way how we do cover the temperature aspect. And within this, you can move a little bit. So you see here, you have a nominal voltage at 70 degrees, you can take it 500 volt for the same lifetime. If you increase a little bit the temperature to 85 degrees, which is typical for the cabinet plus self-heating, you need to lower the voltage to 450 volt DC. And then if you have a pretty high temperature in your environment, let's say 105, so you lower to a 350. But of course, you cannot go over the 105, you cannot go over the maximum temperature of the component, because then the material, in that case, a film capacitor, will melt, it gets soft, and then it will kill it within a second. Other aspect is when you have this voltage levels, and then in best case, the best design would be if you choose only one capacitor in series, but this is in some cases not really realistic. So we don't have this component that provides the kind of capacitance and rated voltage you need. So to cover the voltage, you can obviously put parallel capacitors in series. And I think everybody knows this formula on the top. So that's the way how we calculate when capacitors put in serial connection. But in realistic way is not all these here are the same, which would really simplify this formula. Actually, there are some manufacturing tolerances that could be, minus 30, plus 10%, for example. And also over lifetime, the capacitance change not equal for all components. So what you need to consider in your design when you do something, some of them in series, so you need to consider the tolerance. And this formula above give you an idea about if I have n equal capacitors in series, which what we highly recommend to do. And for example, you're looking here for a 1200 volt application, and you have 3 capacitors, each is 400 volt. We'll give you probably 1200 volt. And you have a 20% tolerance. What happens is, let's say the worst case it could be is, one of them is plus 20% and all the others are minus 20%. And in that case, if you apply this formula, you see your 400 volt component the one with the lowest capacitance get a 515 volt, which is nearly 1.2 times rated. That doesn't mean that the capacitor will explode immediately, but it definitely get higher stress, and this lifetime is definitely reduced compared to the other one. So that could be one of those failure. The solution could be also you're choosing a higher rated voltage, so you have more voltage reserve, or you put more of them in series. That's the other way you can do it. But that, of course, has something to do with cost, and cost typically is the limitation here. So that's the voltage aspect when I put the stuff in series. Second thing we need to consider is the ripple current. And that is very, there's quite often when we do this kind of project, there's a lot of misunderstanding when we talk about current. So what kind of current do we mean? So we have, for the DC link capacitor, actually we have 3 different current terms that going around. And this is not 100% defined. So the ripple current is definitely the one that goes into the capacitor. But when the customer talk about current, that could be either the current that goes into the phase leg of the motor or to the charger of the battery, or it could be the total current that comes from the source, in that case, the battery. So that we really need to drill that down to the ripple current that going through the capacitor. So typically we get some kind of measurement. If you don't have any idea about that, probably starting point will be 65%. Sorry. 65% is probably a good approach, and you can start with that. So why need to care about the ripple current? At the end of the day, it's the self-heating of the component. So the self-heating is, at the end of the day, it's defined by the RMS value of the ripple current times ESR and then times thermal resistance. That square is not correct here. So, in other words, if we get a self-heating about 20 degrees Celsius and we know a thermal resistance and we know the ESR value, then of course we can determine the maximum ripple current through the capacitor. So now we get this voltage aspect and we get some of the current, and now talk about power. So power is actually that what we give you, and this formula based on sinusoidal waveforms. So you can either use the voltage that depending on the frequency, or you go with current and reform the formula a little bit, and then you need tangent delta. And tangent delta, and our American friends, they call dissipation factor. In Germany, we say tangent delta. So that's a relation between the ESR and the admittance of the complex, of the imaginary part of the complex number. So just an example for the polypropylene tangents at 100 kilohertz will be a 0.07%. So that's quite low. And that is some aspect that's going or speaking for example for film capacitors here. So the switching current for the non-technical guys. That is what we typically expect, and that makes our life pretty easy because I mean we have only to deal with one frequency. That's the thing. If you start something and switch, whatever that is, and what kind of period and duty cycle you have here, then you have, according to some rules of the electrical knowledge science, so you have what's so-called harmonics. That means we have here magnitudes at higher frequencies. So every signal form can be created by a sum of sinusoidal waveforms. And for that one, you have probably 20, 20, 30, whatever. But at a certain point, you need to only take care about the significant magnitude here and divide it. And that's actually what you should do is when you have that, you do kind of Fourier analysis, and then you figure out the harmonics. And then what you do is you start doing the same stuff, but you calculate your RMS value based on a number of harmonics. And from practical point of view, if your design is very robust, probably 3 of them is okay, 3 or 5. I think everything beyond 9 harmonics doesn't really change the result that much. That you end up with, you know, a single percent digit, and they don't really care about the whole applications. So that's the thing you need to consider when you talk about a DC link capacitor. So as I said, we have 3 major families I want to walk through with you and pick a little bit some aspects out of that for the specific technology. Again, I think the cap value is mainly given by your application, depending on the power of your application, depending on the voltage level, and depending on the timing of switching frequency or hold-up time or whatever. For the KEMET standard in industrial solution, we have 2 families that typically targeting this stuff. So that's a box types, and then we have this cylindrical an aluminum can, C44U. And you see here you have this voltage level 500, 1500, and 1 to 210 microfarad in different box sizes up to 52.2. And on the other side, we have the can type, you go for 6 to 1800 volt. So this more or less depends on you have something put on your PCB, then you lose a C4Q, or you have kind of capacitor bank where you have a couple of them in series or parallel. And then you typically go with C44U, which is easier to mount in a cabinet for that kind of stuff. What we are doing here, because we get more and more requests, driven by the automotive industry regarding the e-mobility, we are forced to do some THB, stand for temperature humidity bias. That means we apply 85 degrees Celsius, 85% humidity, and then for 500 or 1000 hours, depending on that. So this is the 2 standard solutions that's available from the catalog standpoint of view. In some cases, you're working for a big company and you have a pretty high volume. So what we are doing is we're doing a brick capacitor. That means we're taking our wounded elements and put them together or assemble them together in a new shape, which is typically a custom development that takes over a year, has a highly invest, so we don't do that for 5 pieces or something. We really need to see some higher business on that, but also in industrial, not only in automotive area. So we do for some construction machine manufacturer. So we have different applications where we have custom brick capacitors ongoing here. And what we are starting typically is we have kind of design program, depending on your requirements. And then we do simulation that actually mainly about the temperature distribution within the component. And then we have, of course, some mechanical things here, in that case, vibration. So we need to check if you don't tear away the terminal when it's getting a shaky environment. And then because simulate is good, but then we need to prove the simulation, and then we do an evaluation. So what you see here, the blue stuff, that is actually thermocouple element that we can place within the component and then get an idea about the hotspot temperature. And from the hotspot temperature, we derive the lifetime of the component. So what is the trick here with the brick capacitor? So if you require thermal cycling, then we need to have a special design here, because the coefficient of thermal expansion of the bus bar here and the winding element is 1/10. So that means if you do thermal cycling, and then you tear away that pretty fast off, within a couple of hundred cycles, everything is disconnected. So we have a very special way how we need to consider that, again, depending on your requirement. If you don't have that, don't worry. I mean, the best really solution is if you go with a C4AQ. I mean, this gives you a little bit more flexibility. And then what I really like on that is that so you can build up kind of modularity in your system. That means for the high power, you probably take 5 box capacitors, and for medium power, 3 capacitors, and for low power, only 1. This kind of flexibility, or you have, need to change your design a little bit. You build a new PCB, and in an urgent case, you can get a new one in 48 hours if you pay for that, of course. But actually, that's a pretty cool way to be flexible and do not depending on this long lifetime cycles on that. And in the KEMET world, we talk about C4AQ, C4AU, that's the temperature divided, that all these box capacitors. And what's new here in that case is actually that we have a low profile solution, because we get some requests from the market which claims that the capacitor box is too high. So now we can lower that down to a minimum of 12.5 millimeter. What happens if we simply flip that box a little bit by 90 degrees? So that's normally would be the way perpendicular to the PCB, and in the other case, I think the PCB would be here, not here on the bottom. And one thing what really excites me, even for this high power thing, is that we are working on the C4AQ. So we're working on a press fit solution. So the story here is if you want to solder the box capacitor within, this massive copper inlay for a high current PCB, you need to spend a lot of energy. And so most of the energy probably goes into this copper inlay and not melting the solder to create this connection to here, or lots of energy going into the wire and then melts the connection to the winding element. So, and the workaround for that, and I think it's the best solution for me, is we have a press fit solution. So that is what we have available. So we're looking for partners, we're working together, starting this new technology and creating some really nice, unique applications using this press fit connection. All right. So that was film capacitor. Let's talk about aluminium electrolytics. So that actually is a new thing. We have a couple of different families. So we have snap-in capacitors, we have through-term capacitors. I think the major decision is about 85 or 105 degrees C and your lifetime requirements. That actually leads to a couple of families, and so depending on your application, you can either use the snap-ins. You see the similar voltage level, and then we have screw terminals. So that's a pretty huge bank with high power banks, sometimes used for submarines in this kind of application. And for the low voltage parts, you see 600 volt here, and it's 25 up to 450 DC. That's a special family that's made in Portugal here, and actually is really going mostly in the automotive. And we have some street light lamp applications running with that, because it's a very long life capacitor. The pretty exciting news on the aluminium electrolytic is about 630 volt, which actually targeting the 1100 volt rail, which was before that. I mean, you get 350, 400 volt, you need 3 or 4 of them in series, which is a little bit tricky. And right now you need only 2 of them, because we cover this 630 volt voltage level. The other nice development is about a rectangular capacitor, which we do in collaboration with another company. So that's pretty cool, because This is a pretty unique design and gives you a completely different, um, opportunity to have a mechanical built capacitor bank in your circuit on that case. Again, this is a metallic case. It's just an aluminum can, but in form of a rectangular shape, and it's really exciting. And on the lower level, so what we're actually doing is, in terms of improvement of the technology itself, we introduced the hybrid polymer technology. So it means that one here is a 48-volt system. So you see a bunch of them. So that's everything you can probably cover with aluminum polymer hybrid. And what we see in KEMET is all this new development going into an SMD component, which does not mean that the old one is obsolete. There's enough of them and enough property and application going for axial and radial hybrid polymer and this PEG low voltage level. But again, this is pretty new. And the cool thing is we have this a very special, you see here the difference, that actually a KEMET pattern, we have a vibration-proof design that helps us also to promote this in a mobile equipment, at the end of the day automotive, but it's also for industrial equipment that's somehow driving or moving forward. All right, not forget this lifetime calculation is always a topic. So we have this online tool available, and the good stuff is you can add emission profile. The only thing you take care about this is that the time fraction in total must be 100%. Otherwise, you get a small triangle that makes you aware of that doesn't fit on that. So, and then you plug in your ripple current couples, tuples, and then you get a certain lifetime, and you get all this calculation steps in between here on that case. Last not least, the ceramic stuff, power ceramic thing. That's what I'm told the father of, because I voted this some years ago. Actually, it's called K-sealing. It's an alliteration to de-sealing capacitor. That's a ceramic material. It's actually a COG, which has a really nice temperature range. So it can go up to 150, which you don't cover with for high voltage, and 150 degree you can't cover with the aluminum electrolytic or the film capacitor. So that's kind of area is definitely for this product. And of course, the very high voltage and really stable capacitance over lifetime. So, and it's really predicted for usage in wide bandgap application, where you drive the switching frequency to higher levels. And that means 100 kilohertz, 200 and 300 kilohertz in that case. In addition to that, and you see that here, a small one, and now it's a little bit bigger, we have established a new technology that we call Connect. And Connect is something that is, so we bond the capacitor here on the termination area with a special material we call TLPS. It's a transient liquid phase sintering. That allows us to build stacks without a lead frame. And when you put them upright like this one here, you get some amazing properties. At least you lower the ESL and the ESR of your component, and you can drive an incredible amount of current to that. For that one, the 1812 here, the 3-point chip, you can drive 30 amps in a 4-point something 3.2 millimeter chip on that case. We have fully established that now in our online simulation tool, which is going now in the version 3. And you see you have different options for graphs, so capacitance, inductance, current voltage, SPICE model, temperature rise, capacitance, etc., etc. So you can pick up all the details for the component to get an insight or get a better understanding how it will work in your application for that. And with that, yeah, I think that's a summary. We have the 3 technologies, film capacitors, electrolytic, and K-sealing. Depending on the voltage level, depending on the required capacitance and the power you need, you probably move in 1 or 2 directions. And if you are not sure, or you have any doubts, or you need any support, my colleagues and myself are available to support you and give you the right guidance. And as much as we know the application conditions, requirements, and the more we know, the better will be the result of our recommendation, what you should put in your circuit on that case. And with that, Alex, my friend, give me a thumb up, because I really hit the 30-minute, which is very rarely the case for my presentation. Martin, is there any questions in between?
Yeah, thank Alex for the presentation. It was very interesting.